What's the typo? It doesn't look right. Okay, you could, oh. Yeah, I think you are right there because I think this should be a CO2. Does that make more sense? I think that should be there. So I would need to fix that. Anything else? I would like to remind you that in this review, not only are there 100 bajillion multiple choice, but on page 33, you hit the written response. And your test will have 24 multiple choice questions. Okay, 24 multiple choice questions, and it will have 16 written response marks.
Oh.
Which is usually somewhere between 3 and 7 questions, okay, depending on the value of each question. Usually more like 4 to 7 questions. I would say most likely between 4 and 6 questions. Yes? Other than working through the review and taking study notes for yourself? That's what I would do. I would also the vocabulary sheet that I gave you back at the beginning? Okay, I would go through there, make sure I have those all visualized well. So the vocab sheet is nice for, making sure you kind of understand the concepts. Going through that what's on the test and saying, oh, could I do that? What it says? You know what I mean? So the vocab sheet, the what's on the test. Do the written response questions. Yeah? Because usually people are like, multiple choice. Ooh, easy, gimme. Because you get that little hit, right? That little dopamine hit. I finished a question. Look at me, right? But the written response is like, oh, I got to write all this stuff. And it's just not as satisfying, right? So don't forget the written response. Other than that, if you want extra study material, like if you're like, I've done all 127 questions and I've also done all the 25 written responses, you could look in Hebden. Hebden's got lots of stuff in Unit 1. Yeah? Okay, yeah. Study with a buddy. Those would be my suggestions. I didn't do lots of studying with a buddy though in university because I found we got distracted more than whatever. I like to study with a buddy when I didn't understand things, but if I understood it mostly, then I kind of just wanted to plug away on it on my own. Yeah? Oh, do you guys know about the Pomodoro?
Yes.
It's where you work for 25 minutes. And then you take a break for 5 minutes. Yeah? And when you take a break, you physically get up and you move around. You can do some stretches, get a drink of water, go to the bathroom, whatever, but you're not at your workstation. Okay? It's not like I take a break and I go on my phone. Phone is not a break. It doesn't do the same things to your brain as, going out and looking at the sunshine in the sky. You're like, oh, blue sky. Right? That'll make you feel better. Cross-body motion, where you touch one side of your body with the other side. Why on earth would you do that? It helps connect your two hemispheres so they work better together. You can also do that by doing silly things like crawling, because when you crawl, right hand, left foot, or left knee, go with left hand, right knee. Or you can be like, And when you have your one part of the body cross over to the other side of your body, it, like I said, it connects those things. I used to study while drinking a cup of mint tea. And then on my test, I had a mint tea bag and I would smell it while I was writing my test. So that it would maybe bring back memories. I'm like, I don't know, scent helps you, right? What else would I do? I would have an apple right before a test. So I would get like a nice little hit of glucose, but it wasn't like a candy bar. So it would kind of last throughout the test. I would go for a walk around so that my blood got flowing before the test, right? All sorts of those little tips. All right. Any other questions? Okay. Then we are going to go to page, I think it is 27 in the blue book. Let's see if I'm correct. 27. Not that one. Blue book. Yeah, maybe it was 27. Yeah, there we go. Yeah, it is 27. Okay, so when last we left, we were on page 27 and we had filled in all the data for this particular question, and today we're going to solve it. So our initial concentration of the butane is 10 molar, then we have 2 molar, or you could have done 1 molar and 0.2 molar. You could have done 100 molar and 20 molar, because if you recall, the question said that we used at the time that we're interested in, we had used up 80% of the reactant. So how much reactant was left? 20%. If we've used up 80, we have 20% left. And we are now making an assumption. Easiest assumption would be that we have 100 molar and 20 molar, but those are like really weird concentrations. We don't get concentrations that high. So a nice 10 molar, 2 molar, or a 1 molar, 0.2 molar are good. The other thing that is nice about 1 is it's super easy to do calculations with. So I'm going to probably choose that one when I go to do my calculations. In the question, we were given the value of K, the rate constant, and we were told that it is first order, and we want to find the time. So we decided out of our 3 equations that we were going to use equation B, which is the first order equation. And it is up to you whether you solve for T first and then plug in your numbers, or whether you put in your numbers and then solve for T. Okay? I think it works equally well for this question to do it either way. When you have the 1 over, it's easier to solve for 1 over whatever it is and then just find the reciprocal. Okay, but this one is a ln. Do you guys think you could plug your numbers in here and see what you get? Go for it. The numbers you're plugging in are the ones that we wrote up there. Okay. What do you guys think about my answer? Sig figs. Okay, now, because we were doing like an 80% and 100%, I'm going to ignore the sig figs and those things because they were kind of vague. This would probably be an instance on an AP exam if they were to give you something like this, which they won't. They probably would not worry about sig figs in the marking key. Okay. Sometimes they look at sig figs and sometimes they don't. So did I talk about this yesterday with you guys? Yeah. Okay. So when in doubt, go with 3. But in this case, I would probably go with 2 because there's 2 there. And 80% kind of looks like 2 sig figs also, right? I know it's not 80 dot, but do you think they're saying 80 or do you think they're like, maybe it's 81? Maybe. No, it's probably 80. Okay. Anywho, you do that. And so we should now have 170 seconds or 1.7 times 10 to the 2 seconds. Is good? Okay. So the rest of them are basically, instead of solving for t, we could be solving for either a at time t, how much is left, or we could be solving for initial concentration. So let's take a look at how much remains after a given time. So that's going to be the concentration of A at time t. In other words, i.e., concentration of A at time t. And we're going to go through this one because even though it's just a plug and chug, do you know what I mean by plug and chug? You plug in the numbers and then you chug through them on your calculator. The algebra is a little funky, and so are the units. So we're going to go through it just so you can see that happen. Okay, so we are given the initial concentration, A naught. We are given the time, we're given the order of the reaction, and we're given K. So let's see what those are. The reaction of butadiene gas with itself is as follows. 2C4H6 goes to C8H12. The reaction is second order. So I can say I've got second order. It says my rate constant is 5.76 times 10 to the negative 2 liter per mole per minute. So we're going to fill that in. For our rate constant, that is 5.76 times 10 to the negative 2 liter per mole per minute. You don't have to write out your given information like this, but if you find you're getting stuck anywhere or confused anywhere, it certainly can help to have everything nicely organized, right? So you're not like, oh, what was that number again? We have 0.2 molar, and that is our initial concentration. So that's going to be 0.200 molar. And we want to know the concentration remaining after 10 minutes. So this is 10.0 minutes. And we are at time t. That's what we don't know. We don't know how much molar that is. Which rate law equation will we plug into? First, second, or third? Third, because this is second order. Do you guys want to go and solve that for A at time t? Okay. What did I just do? Oh yeah, no, that's okay. Uh-oh. Did I round wrong? Oh, I don't even have the right sig figs. You okay? Is my answer wrong? It could be. Let's see what I got here. 5.6 times 10 to the negative 2 times 10 plus 1 divided by 0.2 is 5.56. And then when I take the inverse of that, I get 0.179, which is what I got when I did it last year. So am I good? Yeah? Okay. But it should be 0.18 because we've got 2 sig figs here, and I don't know how I missed that. Yes. $5.76. Oh, good Lord. That would be the problem. 5.76. I just can't read and copy. And that would do, and now I don't need to fix it. That's why I didn't see the fit. I did this yesterday with the other class, and I'm like, why didn't I catch the sig figs pass back then? And why wasn't I rounding? Yeah, you're right. It should be 7.6. Thank you, thank you. And that'll give me a different number there, 5.76 e to negative times 10 divided plus 1 divided by 0.2 equals 5.576. Okay, that's better. Anyway, I don't know why I'm doing this because it's probably on the next page. No, it's not. No, it is. Is it? No. Oh, well, that's okay. There is a third example here where you're finding the concentration that was initially present. Do we want to go through that, or are we like, we're good, we've done enough algebra for today and we can believe that we can do it? We can believe we can do it? All right, we're going to move on then to section 1.6e on page 32, half-lives. Have you heard of half-lives before? They used to do them in grade 10, but I don't think they do anymore. So a half-life is the time it takes for a reactant concentration to decrease to 1/2 of its original value. So if you start with 1 molar, it's the time it takes to get to 0.5 molar. And then the next half-life would be the time it takes to get to 0.25 molar. And the next half-life would be the time it takes to get to 0.125 molar. And sometimes the half-life is consistent and it's the same. Radioactive decay always has the same half-life. Other times the half-life changes over time. So if you recall, we can tell the order of a reaction by looking at the graph of A versus T. Okay, so 0th order, the graph is straight when we have concentration of A versus T. And if we look at our half-life, we started at 0.2 and we finished at 0.1. And our first half-life was 34-ish seconds. Yeah? Does that make sense? We went from 0.2 to 0.1. That's from here, this time to this time. From 0 to, I don't know, like I said, 34-ish. Approximately 34 seconds. Our second half-life, if we assume that this is 34, then our second half-life here, the time it takes to go from 0.1 to 0.5, our second half-life, that is from 34 to 50. So our second half-life would be 50 minus 34 is 16. Is that right? Yeah, 16. Okay, and our third half-life would be the time it takes to go from 0.05 to 0.05, and we can figure out what it is. But it doesn't actually matter what the numbers are so much. What matters is that the half-life decreases as the concentration decreases. Half-life decreases as concentration decreases. If you have a first-order reaction, so this would be another way to tell from a graph what order you have. Yes? If you saw this curve, you could say, oh, well, I need to graph ln of A versus time to see if it's first order, or I need to graph 1 over A versus time to see if it's second order. Or you can use the fact that for first order reactions, the half-life is constant. And you can be like, oh, look, the time it took to get from 0.2 to 0.1, half the concentration, is the same as the time it took to go from 0.1 to 0.5. Those two times are the same. Okay, so if you were arguing this on an exam, you could say, I noticed that the first half-life is 34 seconds, and the second half-life is 34 seconds, and the third half-life is 34 seconds. And I know that a first-order reaction has a constant half-life. Yes? For second order, half-life actually increases with decreasing concentration. So again, you wouldn't necessarily have to graph this if you remember that. If you remember that as half-life, if half-life is increasing, you have second order. I find that kind of hard to remember, so I never bothered, but it's an option for you. You can say half-life is increasing here. The first one is only this many seconds, that many seconds, that many seconds, and so therefore I have a second order reaction. Okay, so you can tell that a reaction is 0th order if A versus T shows that the half-life does what when concentration decreases? Decreases. You can tell a reaction is first order if A versus T shows that half-life does what with decreasing concentration? Remains constant, stays the same, or remains constant, but I am writing big, so I'm going to use shorter words. And you can tell if A versus T shows that half-life increases with decreasing concentration. Okay, so that's information you can get from a half-life. To be honest, I don't care. I don't think AP cares if you know the relation between half-life and the decreasing concentration for the various orders. I've never seen a question about it, but it could be something you could use if you want to, okay? I believe that really AP mostly cares that you can deal with first order half-lives. Those are the kinds of questions I usually see about half-lives. And the three things you need to know, one of them you already know. For first order, you know that the half-life is constant. Uh-oh. Uh-oh. Let's not plug you in. Let's hope you work. Okay. So for first order, half-life is constant. You should know that radioactive decay is always first order. So if they're talking about, you know, carbon-14 dating, have you heard of carbon-14 dating? Okay, and that uses the half-life of carbon-14. That's going to be a first order decay process. Okay. And you should know that the formula given for the half-life for first order is given in the data table. And that is T1/2 is equal to 0.693 over K. So what that means is that given the half-life, you can find the rate constant. Given the rate constant, you can find the half-life. So here is some radioactive decay. This is cobalt-60, which is a radioactive isotope. All right, and this on our y-axis, we have the percent remaining. But we're also showing you the grams of cobalt-60. Hello. Who are we here for? We're here for Sally. She's here today. There you go. Just whenever it's convenient. Okay, so you can see we go from 100% up here at 10 grams to 50%, which is 5 grams, and then down and down and down and down. And you can see what is happening with your half-life. The half-life is, well, there's one half-life here. And in fact, they haven't even given us times at the bottom. They are giving us the number of half-lives. Each half-life has an equal length. So we can actually plot half-life on the x-axis. Is this making sense? So in a sample of cobalt 60, you might have 10 grams of cobalt 60, and then it would decay and decay and decay until you've got very little left. Okay. For cobalt 60, its half-life is 5.27 years. 50% of it will remain after 5.27 years, one half-life. 25% after 2 half-lives, or 10.54 years. And after 3 half-lives, in other words, 15.81 years, 12.5% will remain. Radioactive decay, as said before, follows first-order reaction kinetics. A simple way of solving some half-life problems is to just write out the times and the amounts at each half-life. So if we are given in a question that sodium-24 has a half-life of 15 hours, so our T1/2 is 15 hours. We start with 64 grams, and we're working in hours, so at 0 hours, we have 64 grams. We're going to fill in the chart for how much Na24 we have after each time interval. Could you guys do that? I should have put grams here. Do you guys get what I got? So if they ask you something like, what's the mass of sodium remaining after 60 hours, usually they'll pick like a certain number of half-lives, like they won't give you some weird number, okay? They'll probably give you a half-life. You can just say, oh, how much is remaining after 60 hours? 4 grams is remaining after 60 hours. Now, you can also use the half-life formula and the integrated rate law. All right, so this is a case where, you've got some ickier numbers. All right, and you can say, we could derive the half-life formula by doing some algebra on the integrated first-order rate law, but there's no time for that. So let's just use those formulas. Half-life is a first-order reaction is 35 seconds. So T1/2 is 35 seconds. And I would like you to A, calculate the rate constant. So you'll say, oh, I want to find the rate constant. I am going to use this equation and solve for K. And then plug in my T1/2. So go ahead and do that.
Because I have to help with the
Mm-hmm.
flag.
Yeah, no problem. And don't forget to show your units in your work because that's going to tell you that the unit for K is seconds to the -1 because seconds is on the bottom. Yeah? Our second question is calculate the time required for 95% of the sample to decay. Okay, so we want to calculate the time required, T, for 95% to decay. And I don't know, I've shown all the work here. Shall we just zip through it? Okay, let's zip through it. So this is again a case where we have 95% is gone. So how much is left? 5%. And what does that 5% represent? Concentration of A at time T. Okay, except for we're going to want to put it in molar. Okay. So just like we did earlier, we're going to say, let's let our initial concentration equal 1 molar because this is first order, a natural log of 1 is 0, which makes our math lovely. But you could use 10 and you could use 0.5. Yeah, or you could use 105 and whatever, but we're going to use 1 molar and we're going to use 0.05 because that's 5% of 1. All right, and then you throw everything in to your rate law equation. And remember, because this is radioactive, so it's first order. So we use the ln. In this case, I solved for T before plugging everything in. You take your final concentration minus your initial concentration and you divide by the time. And where did that time come from? That time came from up here. Now you'll notice, did I use 0.020 for the time? Or did I use my unrounded value for the time? I used the unrounded value. Why? You can end up with a rounding error later, right? If you round every single time, what if the rounding always has you rounding up every step along the way, right? What if you have 4 steps and you round up and up and up and up? Now you're way off, yes? So use unrounded values to get your final answer and then put your final answer in correct sig figs. Sometimes it doesn't matter, sometimes it does. And you can't predict which case it's going to be in any one place. So, and then we just sort through the numbers and we get 150 seconds. Ooh, we're going to be sure to make a let statement or an assume that statement. Important. You're going to say let the concentration of A naught equal 1 molar. Yes? Or you're going to say assume concentration of A naught is 1 molar. Because is the initial concentration 1 molar? No. So if you just say concentration and the initial concentration is 1 molar, that is an incorrect statement. You're making that assumption so you can actually do some math with it. Okay? So we now have, or assume, that would also be fine. Example number 3, the rate constant. So we have the rate constant. So this right here is K. What is the half-life? And we say, radioactive decay is first order, and that's the one that they give us in the data booklet. And we just throw our numbers in there and we get a final answer. Just make sure that when you are doing it, you show your units, because then you'll get the right units at the end. Okay? Example 4. Radioactive isotope copper-64 is used in the form of copper-2 acetate to study Wilson's disease. That sounds like a lot of information I don't need. What I do need to know is that my half-life, my T1 half, is equal to 12.70 hours. What percent of copper-64 remains? So what are we being asked to find? The amount that remains is the concentration of A at time T. And because they're doing a percent here, I would be really, really tempted to just use 100 for my initial concentration and have it be solved for the other one. Okay, so in order to do this, we will want to use an integrated rate law to solve for this. But in order to use an integrated rate law, we need K. Well, what can we do for K? Oh, it's radioactive. Isn't that nice? Because that tells us we can use its first order, and we can use this equation, right, to find K. So now we have a K value. Hooray. And now, because we want to find the amount that remains, remember the amount that remains is always the concentration at whatever time T they're asking about. Oh, I didn't make it 100 here, but you could make it 100. I said, let the initial concentration, remember you need to say let, important. And then we're going to, because it's our first order, we're going to use the first order integrated rate law. I solved it for ln of AT, right? Because we're trying to find A at time T. And then once we've gotten there, you could, if you know what you're doing with natural logs, you could go straight to solving for A at time T, but I'm just going to solve for ln of A at time T. So we know that ln of A at time T, we throw in all our numbers and we get negative 0.3492. Now, how do we go from ln of A to regular A? On your calculator, above the ln button, wherever the heck that is, I don't even know where it is in my calculator. Oh, there it is. Usually it's the second function of ln. So take a look on your calculator and see if you can find it. The button on your calculator, you'll have the ln button, natural log button, And it'll say e to the x. Homework. Work on these. If you haven't done the review, remember tomorrow is your last day to ask questions about it. So that might be your priority. Okay. And we'll finish up e to the x tomorrow. Okay.